Есть. Хорошо. Okay, our previous lecture was entirely devoted to the index map in K-theory. And at the end of the lecture, we proved that for every extension of Banach algebras, so I is an ideal of A and B is the quotient of A modulo I, for every such extension we have a 5-term exact sequence of the following form. So it starts with K1 of A, then we have K1 of B, K0 of I, K0 of A, and K0 of B. So these arrows are induced by these two arrows are induced by the maps between our algebras. So if this is I and this is P, then we have here I star and P star. And similarly, this map is also induced by P. And this arrow is the index map, or more exactly the map from K1, which is induced by the index map defined on the group GL infinity of B. Okay, so today our first goal will be to extend this sequence infinitely to the left. And on the way, we'll obtain a useful relation between the groups K0 and K1 for Banach algebras. So we start with Banach algebra A. And we introduce the following construction. We define the suspension over A as follows. This is the Banach algebra denoted by SA, and it consists of continuous A-valued functions on the closed interval 0, 1, which vanish at 0 and at 1. Equivalently, we can describe this algebra as the algebra of continuous and the vanishing at infinity functions on the open interval 0, 1. So the isomorphism is quite obvious. Every function in here uniquely extends to the interval in this way, to the closed interval in this way. Sometimes we'll interpret this algebra as the algebra of continuous and the vanishing at infinity functions on the real line. So clearly these algebras are isomorphic because the open interval and the real line are homeomorphic. By the way, let's recall that this is nothing but the minimal tensor product of C0 of R and A. And sometimes we'll interpret the suspension as follows. This is isomorphic to the algebra of those continuous functions on the circle S1 with values in A, which vanish at the base point, say at the identity. Again, this is very easily seen to be isomorphic to this one in the obvious way. Okay. The Russian for suspension is nadstroika. And let's now look at an example which explains why the suspension is so called. Example exercise. Let's look at the commutative case. That is the case where A is a commutative T-star algebra. So suppose that X is a locally compact Hausdorff topological space. Then the suspension over the algebra C0 of X is in fact isomorphic to the algebra of C0 of continuous vanishing at infinity functions on the topological reduced suspension over the one-point compactification of X with the base point removed. So let's recall what it means. So here, sigma of x plus is the reduced suspension over the one-point compactification. And in a general case, you will have a compact pointed topological space Y with a base point Y0, compact pointed topological space. Then the reduced suspension sigma of Y is defined by definition as follows. We take the cylinder over Y, that is multiplied by the closed interval, and then take the bases of the cylinder, collapse them to a point, to a single point, and also collapse the following interval to the same point. So this is the reduced suspension over Y. So geometrically this is related to the non-reduced suspension as follows. The non-reduced suspension is obtained from the cylinder by collapsing the face of the basis of the cylinder to points. So we have 2 points here. This is the non-reduced suspension, and the reduced suspension is obtained from here by collapsing the following interval to a point. So this is the reduced suspension. Okay, so let's now come back to Banach algebras. Let's recall that some time ago we defined the cone over a Banach algebra A. The cone over A is the algebra C of A, which consists of those continuous functions on the closed interval 0, 1 with values in A, which vanish at 0. And let's now observe that we have the following Banach algebra extension. So the algebra A is isomorphic to a quotient of the cone by means of the evaluation of the identity. Clearly this is surjective. And the kernel of this map is nothing but the suspension, S of A. So the suspension becomes an ideal in the kernel. Why is it useful? Well, we have the following result, theorem 1. The index map associated to this extension, index map associated to this extension, well, let's denote it star, is in fact a natural isomorphism between K1 of A and K0 of SA. So this isomorphism relates K0 to K1. So it interprets K1 in terms of K0. The proof is very short. We simply look at this 5-term exact sequence. Let's denote it by, say, E. We look at this exact sequence and apply it to our extension. So what do we get? Let's recall that the cone is contractible. So K-theory of the cone is trivial. So if we substitute this extension here, we get 0 here, 0 here. And here we have an isomorphism between K1 of A and K0 of the suspension. So we simply apply our exact sequence to our extension and use the fact that C of A is contractible. So it has trivial K-theory. As a simple corollary, this is corollary 1, we get an interpretation of K1 in the commutative case. So if we substitute here the algebra C0 of X, where as usual X is a locally compact Hausdorff topological space, then it is isomorphic to K0 of this algebra, that is to the topological K0 group of the space sigma of X plus minus the base point. Sorry, I forgot to remind you what the base point of the reduced suspension is, but it's more or less obvious from the construction. Of course, this point, which is obtained by collapsing this subspace to a point, is, by definition, this is the base point of the reduced suspension. So we remove this base point and get the topological K-theory of this space. It is not necessarily compact, of course, because we remove a base point from something compact. But we can also interpret it as the reduced topological K0 group of the reduced suspension, where the reduced K-theory, K0 of a pointed compact space, is defined to be the kernel of the canonical map from K0 of Y to K0 of the base point, which is induced by the inclusion of the base point into Y. So this is just the definition of the reduced K0 group, which makes sense for any pointed compact topological space. So if I don't put the tilde here, then we get the K-theory of the one-point compactification of this space and of the unitization of this algebra. So since we don't want to take the unitization, we have to take the reduced K-theory here. And by the way, this group is traditionally denoted by K minus 1 of X. This is just the definition. K minus 1 of X is defined by this equality. Another corollary, corollary 2, I have already mentioned this result at the previous lecture as an exercise, but now this is no longer an exercise. This is indeed a simple corollary of theorem 1, namely the functor K1 is half exact, split exact, continuous, stable, product preserving, and K1 of the opposite algebra is isomorphic to the K1 of A. So now, modulo this theorem, this is almost immediate from the respective properties of K0, follows from theorem 1, and the respective properties of K0. Well, indeed, for example, why is it half exact? If we take an extension and apply the suspension, we still get an extension. This follows from the Bartle-Graves theorem, which I formulated at the previous lecture. So we apply the suspension, we still get an extension, and apply K0. And K0 is half exact. For the same reason, K1 is split exact. The only delicate point is the continuity. Let me explain this in more detail. In fact, the suspension functor commutes with inductive limits for the following reason. S of A is the tensor product. And the point is that we can replace here the minimal tensor product by the maximal one, because this algebra is nuclear, by the nuclearity of C0 of R. So some time ago I stated without proof that all commutative C-star algebras are nuclear. This is not an easy result, but this is a classical result of Takesaki, and we use it without proof. And we know that the maximal tensor product preserves, maximal tensor products commutes with inductive limits. This was proved some time ago. And so now the continuity of K1 follows from the continuity of K0. The stability is also clear because we just apply double tensor product. First we multiply by C0 of R and get the suspension, and then we multiply the compact operators. And everything is reduced to the stability of K0. Okay, now we are ready to define higher K groups. So far we had only K0 and K1. Now we can define K2, K3, and so on. And this is done as follows. First of all, we define the nth suspension over A. By induction, as follows. This is Sn of A is defined to be the suspension over Sn minus 1 way. So this is defined now for every n greater than or equal to 2. By the way, let's observe that since S of A is the tensor product, by C0 of R, then the iterated suspension, the nth suspension, is obtained by tensoring by C0 of R n times. And by the associativity of the tensor product, we deduce that the nth suspension is isomorphic to the algebra of continuous vanishing ad infinity functions on Rn with values in A. And we now define the group Kn of A as follows. So by definition, this is K1 of the suspension of the iterated suspension Sn minus 1 way, which is by theorem 1 isomorphic to K0 of Sn of A. So here we assume that n is greater than or equal to 2. Well, since the suspension is a functor, it follows that Kn is also a functor from Banach algebras to billion groups. And combining our results, combining our previous results, we get the following theorem. Theorem 2. For every Banach algebra extension, I, A, B, there is a long exact sequence of the following form. Kn of I, Kn of A, Kn of B. Then we apply the index map and get Kn minus 1 of I, and so on. And in the end we have K1 of I, K1 of A, K1 of B, K0 of A, of I, of A, and of B. So these maps, some of them are induced by I and P respectively, and the remaining maps are the respective index maps. index maps composed, of course, composed with suitable isomorphisms of this form. Actually, there is nothing to prove here. We simply combine our previous results. So we already know that this sequence is exact. Now we know that K1 is half exact. So by the half exactness of K1, we may add K1 of I here, and we still get an exact sequence. And then replace our extension by the extension obtained by taking the suspension, and we get a similar exact sequence from here to here, and so on. So as a result, we get our long exact sequence. Here is a simple illustration of how this works in practice. An example. By using this sequence, we can again prove an isomorphism between K1 of the Kalkin algebra and the integers. Of course, we already know this fact. We proved it two weeks ago by using the Fredholm index. But now we can obtain it as a trivial corollary of this long exact sequence. We simply apply it to the Kalkin extension. Consider the Kalkin extension. So the compact operators are embedded into the bounded operators, and the quotient is the Kalkin algebra. And apply our let's look at the respective segment of our sequence, namely the following one: K1 of B, K1 of Q, K0 of K, and K0 of B. So we know that K0 of B is trivial and that K1 of B is trivial. So the index map is an isomorphism. But on the other hand, we know that K0 of the compact operators is isomorphic to the integers. And that's it. So this is an isomorphism between K1 of Q and the integers. Now our next goal, and this will be the final goal of our course, is to discuss probably one of the central results, or maybe the most fundamental result of K-theory, namely the Bott periodicity theorem. So the theorem, the statement is very short. It states that there is a natural isomorphism between K0 of A and K2 of A for every Banach algebra A. So as a result, we have just defined infinitely many K functors, but in fact we now see that there are only two of them, because by applying suspensions we see that K0 is isomorphic to K2, to K4, to K6, and so on. And K1 is isomorphic to K3, K5, and so on. So we have essentially only two K groups, K0 and K1. This result is essentially due to Atiyah. It was proved in the 1960s. And it extends the classical periodicity theorem due to Bott, which describes homotopy groups of the infinite unitary group. Atiyah proved actually, why do I say that it is essentially due to Atiyah? Formally, Atiyah proved this result only in the context of topological K-theory, that is, for K-theory of compact topological spaces. And actually, he gave at least two similar but different proofs for this result. But each of them easily extends to Banach algebras without any essential changes. In our course, we'll discuss another proof, which was developed by Kunz in the 1960s. In the 1980s. But before we prove this result, let's look at some illustrations. First of all, we have the following corollary. The corollary is that we can now loop this infinite long exact sequence into a cyclic 6-term exact sequence. So for every Banach algebra extension, there is a cyclic exact sequence of the following form: K0 of I, K0 of A, K0 of B, K1 of B, K1 of A, and K1 of I. So here we have maps induced by I and P respectively. This is I star, P star, I star, and P star. And here we have two arrows of the following form. This one is nothing but the index map. And this one is also essentially an indexed map modulo with the following identifications. So K1 of I may be identified with K0 of the suspension of I by theorem 1. And K0 of B, first we may identify it with K2 of B by the Bott periodicity, or with K1 of SB, K1 of SB. And here we have the index map associated to the extension obtained by taking the suspensions. So after we identify this group with this one and this one with this one, this arrow will be just the index map from here to here. Well, indeed, this is immediate from the Bott periodicity and from the long exact sequence obtained in theorem 2. The Bott periodicity and the cyclic 6-term exact sequence they are very important, very useful tools for calculating K-theory of concrete algebras. So let's look at some concrete examples. Example 1. Let's calculate K0 for the algebra C0 on Rn, or equivalently K0 of topological K-theory of Rn. So C0 of Rn is just the nth suspension over the complex numbers. And so by our definition, this is Kn of C. And by using the Bott periodicity several times, we see that this is isomorphic either to K0 of C, this happens if n is even, or to K1 of C if n is odd. And we know that K0 of C is isomorphic to the integers, and K1 of C is 0. So this is if n is even, and the second one, it happens if n is odd. And similarly, we can calculate K1. Similarly, K1 of the same algebra, which is the topological K-theory K minus 1 of Rn is isomorphic to the this is 0 if n is even, and is isomorphic to the integers if n is odd. Example 2, let's now take the unitization of this algebra. Example 2. The unitization of the algebra C0 of Rn is, let's suppose this is isomorphic to the algebra of continuous functions on the one-point compactification of Rn. And of course, the one-point compactification of Rn is known to be homomorphic to the sphere. So we get the algebra of continuous functions on the n-dimensional sphere. And let's also recall that K0 of the unitization of any algebra is isomorphic to K0 of A plus the integers, more or less by the definition of K0 for non-unitary algebras. So combining these facts, we see that K0 of the algebra of continuous functions on the sphere, or equivalently the topological K0 functor of the sphere, is isomorphic to, we simply add one more copy of z here, and we get z squared if n is even, or z if n is odd. Similarly, we can calculate K1. So let's recall that K1, in contrast to K0, K1 is insensitive to the unitization. We have such an isomorphism. And so K1 of our algebra of continuous functions on the sphere, which is the same as K minus 1 of the sphere, is isomorphic to this is 0 if n is even, and z if n is odd. By the way, a useful exercise, find the generator, well, find or describe the generator of K1 in the case where we deal with the circle. Actually, this is a very concrete function of the circle. Well, I can actually, you can guess the answer. The answer is just the identity map of the circle. The inclusion map of the circle into the complex plane is the canonical generator of this group. Okay, example 3. Example 3. We take any Banach algebra, and let's look at the algebra of continuous functions on the circle, and here we interpret the circle as the one-dimensional torus for convenience, with values in A. How can we describe the K-theory of this algebra? Well, let's look at the following extension. Here we have the evaluation map at the identity. Clearly it is surjective. And the kernel of this map is nothing but the suspension over A. So we obtain this extension, and let's observe that this extension splits. Well, indeed, we can embed A into here by constants. And this will be a section for this map. So the extension splits. And now by using the split exactness of K-theory, we see that K0 of our algebra, C of TA, is isomorphic to K0 of this algebra and this algebra, that is K0 of A, plus, and K0 of SA is nothing but K1 of A. So we have such an isomorphism. And similarly, if we calculate K1 for the same algebra, so K1 of this algebra is K1 of A plus K1 of the suspension. But the Bott periodicity theorem implies that K1 of the suspension is K0 of A. So again, we get something isomorphic to K1 of A plus K0 of A. So these isomorphisms reduce the K-theory of this algebra to the K-theory of A. And in particular, we can use these isomorphisms to calculate K-theory of the torus, of the n-dimensional torus. Well, indeed, in particular, if A is the algebra of continuous functions on the n-dimensional torus, then C of TA is, let's recall that it is isomorphic to the algebra of functions on the product T by Tn, that is on the n+1 dimensional torus. Here we can use induction over n. And deduce that K0 of and K1 of the algebra of continuous functions on the torus is isomorphic to z to the power 2 n minus 1. And this is the same as k minus I topological k groups of the torus. Well, indeed, this is true if n equals 1 by our previous example. It follows from here. This is true if n equals 1, and then we just use induction and these two isomorphisms and get this formula for arbitrary n. By the way, the same extension can be used for other purposes. Here's a useful exercise. For every Banach algebra A, the group K2 of A, which is the same as K1 of the suspension over A, is isomorphic to the fundamental group of GL infinity of A. And the base point is the identity. This isomorphism may be compared with another isomorphism which was discussed 2 weeks ago. So let's recall that K1 of A is isomorphic to P0, to the group of components of GL infinity of A. So K1 is isomorphic to P0, and K2, which is, by the way, K0, by the Bott periodicity, is isomorphic to the fundamental group. And the hint is to use the same extension. Well, let's denote it by double star. Let's now calculate something non-commutative. So in the previous examples, we considered only commutative C-star algebras. Now let's consider something non-commutative. This is example 4. Let's denote by A the following algebra. It consists of continuous functions on the half line from 0 to plus infinity, including 0, with values in the 2x2 matrices, M2, such that the matrix F of 0 is diagonal. Well, this algebra may seem a bit artificial, but in fact, it is isomorphic to a very standard and classical object, namely to the cross product algebra, the cross product of C0 of R by the action of Z modulo 2. This is the cross product. unfortunately, we don't have time to discuss cross products in our course. So roughly, if we have a group acting on a sister algebra by star automorphisms, then we can construct a certain universal object out of this action, which is called the cross product. So in our situation, z over 2 acts on the real line just by multiplication by -1, just the symmetry relative to the origin. And this action extends to the action of the same group on continuous functions. So let's now calculate K-theory of A. By the way, this is the first example where we use the cyclic six-term exact sequence. Let's observe that the evaluation map at 0, the evaluation map at 0, takes our algebra onto the diagonal matrices. And the diagonal matrices are isomorphic to C squared. So this is surjective, clearly, and the kernel is nothing but the algebra of functions which vanish at 0. That is, this is just the suspension over the 2x2 matrices. Let's now look at the respective cyclic six-term exact sequence. K0 of this suspension, what is this? This is K1 of the 2x2 matrices, and K1 of the 2x2 matrices is trivial. This was discussed some time ago. Then we have K0 of A. Then we have K0 of C squared, and K0 of C squared is, of course, Z squared. Then we have K1 of this algebra. By the Bott periodicity, K1 of this algebra is K0 of M2, and K0 of the matrices is isomorphic to the integers. Next, we have K1 of A. K1 of A. And K1 of C squared, which is trivial. So we have such an exact sequence. Now to calculate K0 and K1, we must know something about this map. Let's denote it by delta. So an exercise for you is to show that delta is surjective. Probably the easiest way to prove the surjectivity of delta, this is a hint, is to consider the following subextension. Subextension of this one, which corresponds to those functions which have values in the upper left corner. So the respective subextension has the following form. So it corresponds to the functions with values in the upper left corner, and use the naturality of the index map. By the way, I forgot to say that today we have already implicitly used the naturality of the index map when I said that the isomorphism between K1 of A and K0 of SA is natural. So why is it natural? It is natural because our extension, which was used in the proof, this extension clearly depends naturally on A, and the index map in turn, the index map depends naturally on the extension. So as a result, this isomorphism is natural in A. So this is an isomorphism of functors. So now here, using the naturality of the index map, we can prove, this is an exercise, that delta is surjective. Now the surjectivity of delta implies, first of all, that the kernel of this map, of this one, is trivial. Sorry, not the kernel, of course. This map is trivial just because its kernel is equal to the image of delta, so its kernel is Z, so this map is trivial, and K1 of A is 0. K1 of A is 0. And on the other hand, the surjectivity of delta implies that the kernel of delta is isomorphic to Z. this is a little exercise on algebra. If you have a surjective map of z squared onto z, then by the projectivity of this abelian group, we may lift this delta to a map from z squared, and z squared will be just a direct sum of the kernel and the integers. And so the kernel is isomorphic to the integers. Okay, and again, by looking at this part of our cyclic six-term exact sequence, so K0 of A will be isomorphic to the kernel of delta. The kernel of delta is Z. So as a result, K0 of A is isomorphic to the integers. So this is an illustration how the cyclic six-term exact sequence works. Well, some more examples will be given in our next exercise sheet. And let's now discuss some preliminaries for the proof of the Bott periodicity. Well, so we are going to discuss the proof of the Bott periodicity developed by Kunz in the 1980s. And his proof was essentially based on the Toeplitz algebra. So let's now define the Toeplitz algebra. We denote by H the Hilbert space of square summable sequences, little L2. For convenience, we take L2 over the non-negative integers. There is a standard of normal basis, En, in this space of a normal basis, defined as follows. So we have the identity in the nth slot and the 0 elsewhere. And let's consider the right shift operator, V, on H. Right shift operator. So it takes every square summable sequence and shifts it to the right in the following way. So equivalently, we may define V as follows. It takes every vector EI of the basis to EI plus 1 for every I. And by definition of the Toeplitz algebra, denoted by script T. The Toeplitz algebra is by definition the C-star subalgebra. The C-star subalgebra of the algebra of bounded operators on L2 from D of H, generated by V, generated by the right shift operator. Toeplitz algebra can also be equivalently defined in terms of so-called Toeplitz operators. In fact, this somehow explains why it is so called. So, in the beginning of the 20th century, Toeplitz studied some infinite matrices of not only finite and infinite matrices of a suitable form. Then other people discovered that there exist very natural operators on the so-called Hardy space, such that the matrices of these operators are exactly the Toeplitz matrices. And then it was discovered that Toeplitz operators generate the useful C-star algebra, namely the Toeplitz algebra. But we don't need Toeplitz operators in our course, so we will use this definition of the Toeplitz algebra. So this is the C-star subalgebra of BOH generated by the shift operator. Well, of course, this algebra is. Let's observe that this algebra is unital. T is unital for a simple reason that V is an isometry, and so V star V is the identity operator, so it is unital. And let's also observe that it is not commutative. T is non-commutative because the operator V is not normal. V is not normal. VV star is not the identity operator. To understand better the structure of the Toplitz algebra, let's recall that we have an embedding, a dense embedding of the infinite matrix algebra M infinity into the algebra of compact operators. K is a dense embedding, which takes every matrix unit Eij. This is the inspective matrix unit, to the operator, which may be described as follows. It sends every vector x to the inner product by Ej, and then it multiplies it by the vector Ei. So this is the standard embedding of M infinity into K, which we have already used several times. Let's now observe that if we consider the following element of the Toplitz algebra, 1 minus VV star, this is nothing but the matrix unit E00. That is the orthogonal projection onto the first vector of our basis. Well, indeed, VV star is, so first of all, we shift to the left and then shift to the right. So VV star cancels the first coordinate and keeps the remaining coordinates. And so 1 minus VV star does just the opposite. It keeps the first coordinate and cancels the remaining coordinates. So this is E00. Now let's introduce the following notation. Let's introduce the so-called commutator ideal of the Toplitz algebra, which will be denoted like this. And by definition, this is the closed two-sided ideal of the Toplitz algebra, generated by all commutators. All commutators of elements in our algebra. I claim, and this is our proposition 1, that this ideal, the commutator ideal of the Toplitz algebra, is nothing but the ideal of compact operators. Well, why is it so? First of all, we have this equality. So this is the commutator of V star and V. This is 1 minus VV star. This is E00, and clearly this operator is compact. It is a rank 1 projection. So the commutator of these two operators is compact, and this easily implies, this is a little exercise for you, that the same is true if we take the commutator of any monomial in V and V star. The commutator of A and B is compact if A and B are monomials in V and V star. This follows from the formal properties of the commutator. And by the definition of the Toplitz algebra, the monomials in V and V star span a dense subspace in the Toplitz algebra. So by the density, we deduce that the same is true for all commutators, and so we have the following inclusion. To get the opposite inclusion, let's observe that we already know that E00 is contained in the commutator ideal by this equality. And if we now take any matrix unit Eij, it can be written as follows. First we apply v star to the power of j, then we apply e0, 0, and then we apply v to the power I. Well, indeed, v star to the power j shifts everything to the left by j positions. So the jth coordinate will be in the first position. Then we apply this projection. So all coordinates starting from the second one will cancel. And then we shift by I positions to the right. And this is exactly as Eij acts. But this element, since it's the commutator ideal, and since it is a two-sided ideal, we deduce that all matrix units are in this ideal. And now, since the matrix units are dense, since this embedding is dense, we deduce that all compact operators are contained in the commutator ideal. And this completes the proof of proposition 1. Okay, so this is the ideal of compact operators. Let's now look at the quotient module of this ideal. This is our second proposition, proposition 2. The quotient of the Toeplitz algebra, module of the compact operators, is isomorphic to the algebra of continuous functions on the circle. And here it will be convenient to interpret the circle as the unit circle on the complex plane. And if we interpret the circle in this way, then this isomorphism is very concrete. It takes the equivalence class of the generator V to the inclusion map of the circle into the complex plane. Let's denote this inclusion by the same letter Z. Well, to prove this result, we apply proposition 1. So we take the quotient module of the commutator ideal, and this implies that the quotient is commutative. So proposition 1 implies that T modulo K is commutative. And since T is generated by V, T modulo K is generated by the image of V. It is commutative and is generated by the element that's denoted by U, which is just V plus K, the equivalence class of V modulo K. And let's also observe that U is unitary. V is not unitary. V is in isometry, but V is not unitary because VV star is not the identity. But U is unitary because of this. So if we take now everything modulo of the compact operators, this will be 0 modulo of the compact operators, and so U star will be equal to 1. So U is unitary. As a result, we see that this is a commutative C-star algebra generated by a single normal element. And by the functional calculus, we see that there is a C-star algebra isomorphism between the algebra of continuous functions on the spectrum of this generator, U, and our algebra. And this is just the functional calculus, which is essentially the inverse of the Gelfand transform. To complete the proof, we have to show that sigma of U is actually the circle. It is clearly contained in the circle. The spectrum of any unitary element is contained in the circle. Why is it the circle, exactly the circle? Well, the spectrum of U, so this is we consider U as an element in T modulo K. But we can also consider this element as the element of B modulo K, that is of the Kalkan algebra, by the spectral invariance. So T modulo K is a C-star subalgebra of B over K. And by the spectral invariance of C-star subalgebras, we have this equality. The spectrum of, if you now recall that an element of the Kaufman algebra is invertible, even only if it comes from a Fredholm operator. So we see that the spectrum is nothing but the so-called essential spectrum of V, which is by definition the set of those complex numbers lambda, such that V minus lambda is not Fredholm. V minus lambda 1 is not Fredholm. And it's standard exercise in functional analysis to show that the essential spectrum of the shift operator is the circle. And this completes the proof. So the spectrum is the circle, and this isomorphism indeed takes, since this is a functional calculus, it takes the inclusion map. It takes this inclusion map to the element U. So this is exactly the isomorphism we are looking for. Now, combining propositions 1 and 2, we obtain the following C-star algebra extension. Propositions 1 and 2 imply that we have a C-star algebra extension of the following form. So the Toeplitz algebra contains the compact operators as an ideal, and the quotient is isomorphic to the algebra of continuous functions on the circle. And this is a very useful tool in many aspects of K-theory and operator theory. This is a so-called Toeplitz extension. Toeplitz extension. By the way, this extension doesn't split. And moreover, we have the following result, proposition 3. The map in K-theory induced by I from K-theory of compact operators to K-theory of the Toeplitz algebra is 0. This is a 0 map. In particular, it is not injective because this group is non-trivial. This group is non-trivial. It is isomorphic to the integers. So this implies that our extension doesn't split. Therefore, the Toeplitz extension doesn't split, even in the category of rings. Of course, there are more elementary proofs of this result, but it is also a simple corollary of our K-theory argument. Well, indeed, if we assume for a moment that it splits, then we know that K-theory is split exact, and so this map has to be injective, but it is not injective. It is 0. And the proof is rather easy. So we recall that K0 of the algebra of compact operators is isomorphic to the integers and is generated by any rank 1 projection. So let's take our projection E00, the projection onto the first vector of our basis. So now we have to show that this element, this class, is trivial in K-theory, in the K-theory of the Toeplitz algebra. Why is it trivial? Well, V is an isometry. We have this equality, and of course this projection is Murray von Neumann equivalent to VV star, just by the definition of the Murray von Neumann equivalence. And VV star is 1 minus E00. So as a result, we see that the class of the identity element in the K-theory of the Toeplitz algebra can be written, first of all, we can write it in the following form. V star plus 1 minus VV star. This is true because these projections are orthogonal, and the K-theory class of the sum of two orthogonal projections is the K-theory class of their sum. They are orthogonal. Well, VV star is Mari von Neumann equivalent to the identity operator, so its K-theory class is the same. And 1 minus VV star is 0, is 0, 0. So now we cancel 1 and deduce that the K-theory class of this projection is trivial in K0 of the Toeplitz algebra. So the generator of this group goes to 0, and so the whole map is 0. By the way, we can now easily calculate the K-theory of the Toeplitz algebra. Of course, modulo the Bott periodicity, but this is another nice example of using the Bott periodicity. K-theory of the Toeplitz algebra. Again, we apply the cyclic six-term exact sequence to the Toeplitz extension. So K0 of the compact operators is isomorphic to the integers. Next we have K0 of the Toeplitz algebra. Next we have K0 of the algebra of continuous functions on the circle. And we already know from our previous examples that this is isomorphic to the integers. Then we have K1 of the compact operators, which is trivial. Then we have K1 of the Toeplitz algebra, K1 of T, and K1 of this algebra, which is again isomorphic to the integers. Okay, so what can you say about this sequence? We also know that this map is 0 by the previous proposition. And since it is 0, and since the sequence is exact, the kernel of this map is trivial, and so we have an isomorphism between K0 of T and the integers. So this implies that K0 of T is isomorphic to the integers. We have an isomorphism here. And also, let's now look at this arrow. Since we have 0 here, this arrow is surjective. That's noted by delta. So delta is surjective, but a very simple exercise is that a surjective homomorphism from Z to Z is an isomorphism. So it is an isomorphism. So this map has to be 0, and so K1 of T is 0. K1 of T is 0. So this is another application of the cyclic six-term exact sequence. The Toeplitz algebra has a very useful universal property. This is a theorem due to Coburn. It states that for every unital C-star algebra A, and for every isometry W in A, there is a unique unital star homomorphism phi from the Toeplitz algebra to A, such that phi takes the shift operator V to W. So this result means that, so briefly this means that the Toeplitz algebra is the universal C-star algebra generated by an isometry. The proof is not trivial. Actually, well, the proof itself is not long, but it is based on a very deep and important result in operator theory, the so-called Wald von Neumann decomposition of isometries on a Hilbert space. So roughly, this decomposition theorem states that every isometry on a Hilbert space can be decomposed as the direct sum of many copies of the right shift operator and the unitary operator. And this implies that the Toeplitz algebra has this universal property. Anyway, so we will use this result without proof. And another useful property of the Toeplitz algebra that we need is the nuclearity. The nuclearity of the Toeplitz algebra follows from the next theorem, which states that if you have an extension of C-star algebras, IAB, this is a C-star algebra extension, and if I and B are nuclear, then A is also nuclear. Well, the proof is not very hard, but it is based on some properties of C-star algebraic tensor of C-star algebraic tensor products that we didn't discuss in our course. So we will use this without proof. And as a corollary, we see that the Toeplitz algebra is nuclear. Because of the Toeplitz extension. So the compact operators is a nuclear algebra. This is also nuclear, and so the Toeplitz algebra is nuclear. Okay, so probably this is the right point to make a short break, and then we'll continue with the proof of the Bott periodicity theorem. Ну да, минут 5, наверное, да, минут 5-7 так. Дух перевести.